All right, let's get started. Thanks everyone for joining. We're very happy to have Professor Pierre Sikivie from the University of Florida in Gainesville. Pierre is a distinguished professor of physics over there, got his PhD in Yale, and did a few postdocs at Maryland, CERN, and SLAC. He's a fellow of the APS and got the Guggenheim Fellowship and the IBM Einstein Fellowship not too long ago. He's a world expert on axion. He's probably the world expert on axion, which is a particle that was introduced in the late 70s to solve the CP, strong CP problem. Pierre was one of the first contributor or first to understand their impact in cosmology of the axion and their role as a very promising dark matter candidate. Proposed ways to detect axions in the lab via the aptly named Sikivie process, and lately has been researching their impact on galaxies, and that's part of the things that he'll be discussing today. So without further delay, Pierre, just take it away.
Okay, Francis, thank you very much, and thank you all for coming. And let's talk about dark matter caustics. Okay, it's related to axions. I'm interested in this largely because of the axion dark matter experiment, but actually I'm not going to talk much about axions at all. So let's see. Right, so the main message I would like to bring across is that if the dark matter is any of the standard candidates like weakly interacting massive particles, axions, or sterile neutrinos, then the dark matter is cold and collisionless. And in that case, you should expect that at any place, at any physical location in the universe, including here on Earth, the velocity distribution is a set of discrete flows, one flow, one another flow, a countable number of flows. And also, where the number of flows changes, you have caustics. So you may have a point, you have 33 flows, and next you have 31 flows. There's a surface separating these two regions where the density is very large, and it sort of diverges there. I mean, of course, nothing truly becomes infinite, but it becomes very large. I thought it would be appropriate here to thank my collaborator, Jim Ipser, who is a retired faculty member at the University of Florida, because he's the one who really taught me how to think about this in an efficient way. The basic transition that he made me do and is that to realize that galactic halos live in phase space. And I know phase space is not intuitive for us because we are used to think about ordinary fluids. Ordinary fluids are collision full, like water flowing or air flowing. And we describe it in terms of a density, say, at a location in space-time, and a velocity, and maybe other properties. But dark matter being collisionless is essentially different because at a given location R, the velocity distribution is completely arbitrary because the dark matter, unlike water or air, can flow through itself. Can flow through itself like neutrinos could flow through themselves, or light, in fact, can flow through itself. So if you give the velocity distribution at every physical location, of course, then you're giving the phase space distribution. That is the information you have to give the state of your fluid. And it's much more difficult in many ways because it's a much higher dimensional space. It's a 6-dimensional space instead of 3-dimensional space. And it is also less intuitive because we are not from early childhood thinking about such strange things as phase space. So here is a picture that I like to start off with that you probably recognize because you live in New Mexico where it's sunny, and it's sunny in Florida too, but in New Mexico it's also dry, I think. Anyway, you have nice pools, and on a sunny, breezy day, and you look at the bottom of the pool, you'll see these patterns of light. Of course, then they will be moving very quickly. So this is like a snapshot. And I don't know whether you've ever stopped to think about why you have these sharp lines of light. And so here's the explanation. If it is sunny and breezy, then the surface of the pool is wavy a little bit, and you have light coming directly from the sun. So the top red line is a light coming from the sun, and the light gets refracted at the surface of the pool. So, for example, this ray gets refracted there, this ray goes straight, and this ray gets refracted there. And you notice then that the line at the top goes back and forth at the bottom of the pool. And what that means is that if you plot the light intensity, which I do at the bottom, there's more light here in the middle because there's three. The light gets there in three different ways. So it only gets here in one way, and here in one way. It gets there in three ways. And what's also important to realize is that where you have a fault in this wavefront at the bottom of the pool, you have more light. There's a focusing of the light onto that point. This is similar to taking a sheet of paper and bending it and then projecting it onto the floor. Where you have the fault, there will be more projected paper than elsewhere. So for example, if you travel along this line, the light front goes here, there's a pile up, it goes there, there's a pile up, and then it goes there. And then there are more complicated, these are called catastrophes. This is called a full catastrophe, then you have cusp catastrophe and more complicated structures. Now, caustics, these are called caustics, where the light has piled up. This is a common phenomenon in the propagation of light. A rainbow is a caustic. If you see the stars twinkling, that's actually a phenomenon of caustics. If you see the sea shimmer, that's a caustic phenomenon. And if you work on gravitational lenses, you know very well about caustics. And why do they occur so commonly in light? First, because light is collisionless. And second, the second condition is that the light must have small velocity dispersion. And in some cases, this is true. In some cases, it is not true. But let's go back to this picture. You will not see these sharp lines at the bottom of the pool unless it's a sunny day, in the sense that the light comes to the bottom of the pool directly from the sun. The sun is a point source. I call that state of zero or small velocity dispersion, because if I go at a point right here, you can see my cursor, I hope you can. If I go at the point right here, there's a unique velocity of the light. Actually, this is not quite true because the sun has some size. And so, but let's take the sun to be a point source. Then the light has zero velocity dispersion. And then the caustic would be perfectly sharp. Of course, the actual caustics are less sharp. So if it's not sunny, that is to say, if it's cloudy, then the light comes from all directions. Then it is no longer cold. It has high velocity dispersion, and you will not see this phenomenon. That's the day when you don't see your shadow. So it has to be zero velocity dispersion, what I would call cold light, if you like. And it must, the other property that is necessary is that the flow is self-penetrating, and light is self-penetrating. Now I want you to realize that dark matter, actually cold dark matter, has these these two properties. It is collisionless, and it has negligible primordial velocity dispersion. It is cold. Cold means that if you go in the fluid may be moving, but all the particles move with the same velocity. The velocity may be different from zero, but the velocity dispersion is zero or very small. Because cold dark matter has these two properties, you should expect that it will form caustics. Now, if you were like me before I met Jim Ipser, I was ill-prepared to think about this. Mainly, although we see about phase space in classical mechanics, we don't use it that much unless you work in these specific topics like propagation of light, or perhaps also beam dynamics if you are accelerator physicist. So let's do a little exercise. Okay, let's have a one-dimensional physical space with coordinate x and its associated velocity x dot. And then here is a picture of the state of my one-dimensional fluid. Okay, the velocities on the left are positive. So the particles on the left are moving to the right. And the particles on the right are sitting with zero velocity. Now, if these were ordinary particles like people in a line, and these particles, people over here would be moving forwards, and they would bump into the people sitting there, standing there, and you would have a big collision. Okay, but I'm talking about dark matter. It's self-penetrating. So what does this actually do? The dark matter particles here move to the right. And so I get the picture over here. The thing is, the evolution is completely continuous. So this maps into that. By the way, the thickness of the line is the velocity dispersion, since at a particular location in X, I have distribution, small distribution in velocities. Now, if you like to think of a fluid as having a density and a velocity as a function of space and time, then you are in luck over here, because at every physical position, it has a well-defined velocity, and it has a well-defined physical density, which would be the projection onto the physical space of the phase space density. And you would see that there would be a bump here because of the incline of this line in phase space. But you get other luck over here, because now at a physical location, you have three velocities, actually three distinct flows. At this location, some particles are not moving, some particles are moving this velocity, some particles are moving with that velocity. But also, if you project onto physical space, you have a pileup where you have a fold in phase space. At this location in physical space, there's many particles, because when you project down, well, you have a fold, like at the bottom of a swimming pool. Okay, so it shows that collisionless dark matter will naturally form caustics. Even if there are no caustics to start with, after a while there will be caustics. Also, let me mention that the density here diverges like 1 upon the square root of the distance to the caustic. So if the caustic is right here, it would blow up like this. Now, it doesn't actually go to infinity because of the velocity dispersion. So it gets rounded off, and maybe other things would round it off. So I hope you will travel with me in trying to determine the phase space distribution of cold dark matter in the universe. And of course, it's going to be somewhat complicated because its phase space distribution is a 6-dimensional space and it's very hard to visualize. But let's start with the homogeneous universe. The homogeneous universe is easy to visualize because it's isotropic. So this is the expanding universe, Hubble expansion. At a given time, the velocity is proportional to the distance, right? This is Hubble's law. There is some velocity dispersion, but if you take the standard cold dark matter candidates like WIMPs or axions or KV neutrinos, this velocity dispersion is extremely small and you may as well ignore it. 10 to the minus 12, I'm talking, of course, in the speed of light, excuse me, I said c equal to 1. 10 to the minus 12 times the speed of light, I think that translates into 1 kilometer per year. Okay, so this stuff is extremely slowly moving relative to itself. It may be moving a lot, but it's very cold. And KV neutrinos are a little bit hotter, and axions are extremely cold, even colder than WIMPs. So this line is very thin. I cannot draw it thin enough. So I have to give it some thickness. So this is the homogeneous universe. Of course, this is not our universe. Our universe has galaxies, and galaxies come from density perturbations. So let me look at the universe that is slightly perturbed by density perturbations. Now what happens is that you have deviations from perfect Hubble flow that are called peculiar velocities. Because the universe is not perfectly homogeneous in density, the particles deviate from Hubble flow. And if you are at this location, for example, the particles on the right will be slowed. How does it go? If you at this location, the particles on the right will be slowed down a little bit. The particles on the left will be accelerated a little bit by your overdensity. If you have an overdensity here, and in fact, if you have an overdensity here, the phase space will tend to rotate. You know this from your course in classical mechanics, whether you're taking it or teaching it. In phase space, around an attractive center of force, the particles rotate in phase space. So if there is an overdensity here, the gravitational force from this overdensity will make the particles rotate in phase space. So one attractive potential is Hooke's law, force proportional to distance. In that particular case, all of phase space rotates with a given angular velocity, omega. But here we're talking about gravity. Gravity falls off with distance. And so what that means is that the center is rotating faster than the outside, and the thing is winding up. And here you would then be forming a galaxy, say. Okay, so now we fast forward to the galaxy. Now again, I cannot show the galaxy in all its complexity. I'm going to assume that this galaxy is spherically symmetric, because then again, I can show its phase space in a two-dimensional plot. The coordinate r is here, actually the log of it, say, and then its associated velocity. Now, after this phase space distribution has wound up a lot, it looks like this. And if you are at a particular location, you see that the velocities at your location form a discrete set. 1, 2, 3, 4, 5, 6. If you count them, I think there are 13 here or 15. It has got to be an odd number because it's 1 plus an even number. Because you go from 1 to 3 to 5 to 7 to 9 and so forth. If you are sitting over here, you see a flow of particles that is falling into the galaxy from your side for the first time. Maybe you can imagine that you're sitting in a bathtub and water is flowing in, but the water has to be self-penetrating. So you have water coming in from the front. Say this is this flow here. You have water falling in from the back. And then you have water that fell in from the back, came to the front of you, is now falling back in towards you, and so forth. And you'll have a finite number of these flows. So I think this has very dramatic implications, this logic. At every point in physical space, the distribution of velocity is discrete, not continuous. So if people show you continuous velocity distribution, there is something missing. Of course, you know that if it's many velocities, then a discrete velocity distribution appears continuous. But at a fundamental level, it is discrete. And also, the number of flows can change from location to location. And where it changes, there has to be a large density. So over here, the first outer caustic, we call this outer caustic, where it goes from 1 flow to 3 flows. Over here, you have a large density. You can think of this as follows, this outer caustic. The dark matter fell in, reached a maximum radius, sitting there for a while, and now it's going to fall back in. So, of course, there's more dark matter at this maximum radius. It's a little bit like you take a spout of water and you shoot it up in the gravitational field of the Earth, and you project it onto the vertical. Where do you find the most water? At the top, because the water is not moving so fast there. That's a caustic phenomenon. Now, you may say, yes, but you have idealized this tremendously. So one thing that you could worry about is how many flows there are, because if there are so many different flows, say a billion flows, of course, then effectively it becomes continuous. But no, they're not a billion flows. The number of flows at all locations in the Milky Way is of order 100. Now, where does number 100 come from? I tell you the arithmetic. The arithmetic is that you take the age of the universe, which is like 10 to the 10 years, and you divide it by the time it would take a dark matter particle to oscillate back and forth with or radius or distance to the galactic center as amplitude. And that number is about 10 to the 8 years. And you have to think about this a little bit, but the number of flows is actually the ratio of these two numbers. It's of order 100. So it's not a large number. Now, you say, well, you simplified in another way because you are ignoring the fact that this dark matter falling onto the galaxy already made smaller scale structures. For example, we have in the Milky Way, we have dwarf galaxies and we have the Magellanic Clouds and so forth. But whatever these structures may be, we don't think they have a velocity dispersion bigger than, say, 10 kilometers per second. That would be considered a large number. Since the escape velocity, which is actually the size of this dimension over here in velocity space, is of order 600 kilometers per second in our galaxy. These 100 flows are really within a cube, which is 1,000 kilometers per second on the side. And if their dispersion is 10 kilometers per second, I mean the thickness of these globs falling in the velocity direction is 10 kilometers per second. Of course, in a cube of size 1,000 kilometers per second, you can have 100 flows with velocity dispersion 10 kilometers per second, and they'd be very well separated. So the notion continues that you do have these flows, even though you have small scale structure. By the way, you should feel free to ask questions anytime. I feel always a little bit self-conscious, just babbling on. And I'm not very good at looking at people raising hands. So I hope someone, if there are questions, you can speak up or someone tell me what the question is. Okay. Now, you may have worried about another thing, is that actually when the dark matter flows through the galaxy, it encounters various inhomogeneities in it, for example, stars or globular clusters. And these inhomogeneities will scatter the flow and diffuse them. Well, this is actually the question I worked on we wrote a paper with Jim Ipser. And we showed that the non-inhomogeneities in the galaxies, globular clusters, molecular clouds, are not sufficient to diffuse the flows. So here's the equation. But basically, although you have a phenomenon of diffusion of the flows by being scattered by non-inhomogeneities, there's not enough of those. If the dark matter falls in for the first time, it will hardly have scattered. Basically, what matters is the number of thorough falls. So let's suppose it fell through 10 times, or say 100 times even. Then take 100 times 10 to the minus 6, which you have to get from this equation, and then take the square root. So this is fused over an angle of 10 to the minus 2. If it fell through 100 times, and I'm talking about falling through the center of the galaxy. Okay, so that's not an issue. So then you may ask, and I'm also often asked as well, we learn about galactic halos for n-body simulations. Do they see caustics? Well, actually they do to some extent, but you have to realize that the number of particles in a simulation, even though it's large, is actually very small. In a dedicated simulation, maybe you would have 10 to the 8 particles per galactic halo, which seems like a lot, 100 million. But you have to realize that the phase space is 6-dimensional. So you have to take really the 6th root of this, which turns out to be 21. So the number of particles you have to describe each dimension is very small. 21, you would not think it's very high at all. The other thing about the n-body simulations is and of course this is really related, is that the mass per particle is very large. It's of order 10 to the 5 solar masses. Now, if the dark matter is WIMPs, 10 to the 5 solar masses, I computed is something like 10 to the 54 WIMPs. Okay, that's a very large number. So in the simulation, 10 to the 54 WIMPs are treated as one particle. But I would not expect 10 to the 54 WIMPs going by another 10 to the 54 WIMPs to behave like two particles going next to one another. In fact, you have two-body collisions in the simulations, so-called two-body relaxation, that you do not have in reality. 10 to the 54 is a very large number. It's easy to say, but let me remind you that Avogadro's number is only 10 to the 24. Avogadro's number is a number that tells you the difference between what you see, you know, your neighbor, the table, and what happens at the atomic level, right? 10 to the 54 is Avogadro's number squared. That's 10 to the 48 times a million. So it's a very big number. So to say, if you're in the simulations, if you believe them literally, you have to think that there's nothing happens between this, over this 10 to the 54, or 54 orders of magnitude. Okay, let me argue further. Show you this picture from the book on galactic dynamics by Binet and Tremaine, a very beautiful and useful book. We show this picture of an elliptical galaxy, and these people working like Malin and others, what they do is they take an elliptical galaxy and they block out the light from the elliptical galaxy to look at the light around the elliptical galaxy. And what they notice is that there are these shells of light. And this has a simple interpretation. The elliptical galaxy has gobbled up a nearby galaxy, maybe a spiral galaxy, which is this low velocity dispersion. It falls in. The dwarf galaxy or whatever gets stretched in phase space, right, by the gravitational field of the big elliptical. As I showed, this then gets wrapped around in phase space around the elliptical, in phase space, around the elliptical in phase space. Then you project it onto physical space. Then you project it onto the sky, and you see these caustics. In fact, you can simulate this. The particles fell in this way. They go back and forth, and they make caustics. We call these outer caustics. As I mentioned before, there's a pileup where the particles reach a maximum radius before falling back. And you have actually an alternation of radii here, there, there, there. And actually you see that in these pictures as well. So in my mind, there's very little doubt about this, that this is the correct interpretation of this picture. If so, at any rate, it shows that when the velocity dispersion of the initial galaxy was way too small to erase the caustic phenomenon, number one. Number two, that the scattering of the dark matter and the stars, by the way, maybe I should confuse you. Stars are not dark matter, but in fact, stars have collisionless flow, even though they are ordinary matter. This is because they are little globs that miss each other. So actually stars falling in, I should have mentioned this earlier, behave really like collisionless dark matter and make caustics. And so I was going to say the stars do not get diffused by the inhomogeneities in the elliptical. And so this also shows that diffusion by inhomogeneities is not sufficient to diffuse the flows and erase the caustics. Now, something that you may not be immediately obvious to you, but is true. You can show it by mathematics. So it's true. When you have this flow in and out, you make a caustic, we call an outer caustic, when you reach a maximum radius. But when the stuff falls back in to go over there, if you take all these particles, they must necessarily form an inner caustic as well. You cannot avoid this. And this phenomenon of inner caustic formation was simulated by Arvind Natarajan. Okay, so there are inner caustics too. Now, I like us to visualize this. And now I'm making a picture. I'm sorry, I'm changing spaces on you again. I'm going back to physical space, and I'm showing a two-dimensional cut of physical space for the purpose of showing a caustic formation. So I'm imagining a shell, a spherical shell, not geometrically spherical, but topologically spherical, falling in. And this is part of a flow. You know, there's of course a next shell falling in, and there was an earlier shell falling in. What I'm doing is like I'm going to a river and I'm drawing a white line on the river so as to see how this line evolves when the river flows. So I'm doing the same with dark matter in our minds, okay? So this dark matter is falling in, and I'm going to assume that this dark matter has what I call rotation, overall rotation. Like it is spinning, the shell is spinning. Okay, what's going to happen? This is a sequence A, B, C, D, E, F. Okay, the top is just going to fall down. It's attracted by the gravitational well of the galaxy, and they're going to end up at the bottom. and the top is going to fall up. It's going to end up at the top. And the particles near the equator, they're not going to fall. They actually have the most angular momentum. They're going to fall in and they're going to fall back out. I hope you can sort of visualize this. So if you take the whole, this whole shell and you follow it, the bottom falls down and the top falls up, and then the particles near the equator, they fall in and out. Now you see that this sphere has, in this process, has turned itself inside out, right? Because if you put a little dot inside and you track it, you find that it's outside. So the sphere turns itself inside out, and it's topologically necessary that it goes to a particular point where it pinches off. This is the point right here on one side, and then maybe there on the other side at a different time. So you form this little loop here, and then it pinches off. If you imagine a sphere turning inside out, you think there has to be a crease like that, right? When at a particular point, and this sphere that I'm imagining is just a particular sphere in the flow. And though when this particular sphere turns itself inside out, you make this crease, The crease is actually a permanent feature in the flow, because the next sphere is going to make a crease at the same location. So the caustic is a permanent feature in the flow of the dark matter, just like a rainbow is a permanent feature in the flow of light on certain days. This is a blow up actually of this particular place where the caustic ring forms. Okay, this is this shell, number one. This is later. This is a particular point. It goes to 1, 2, 3, 4. Then you see later it will pinch off right here. Then it will go over there, and then it will go back out. If you take a point outside this little dashed triangle, you'll see that it is crossed twice. Here, and then there. If you take a point inside, this takes a little bit more time, but it's crossed 4 times. And there has to be a caustic surface separating the regions where the flow, there are 2 flows, and the regions where there are 4 flows. And you can analyze this and realize that this is a non-catastrophe called the elliptic umbilic. It even has a fancy symbol called D-4. So this is a permanent feature in this flow. I mean, it's permanent not in the sense that it cannot move, but it cannot jump, it cannot be destroyed. It's very stable. If you take a cannon and you shoot the cannon at the rainbow is unscathed. It's not like a tree. You shoot the cannon at the tree, you destroy the tree or whatever, the building. The rainbow is untouchable. This too, because this is a feature in the flow of dark matter, and you cannot punch it. You can deform it some, but you cannot destroy it. If you want to visualize this in 3-dimensional space, this is a picture of, in the shape of a caustic ring. And this is from this simulations by Arvind Natarajan. So the dots are the location of the caustic where the density formally diverges. If you change the initial conditions, of course, this case was actually symmetric, but if you change either the potential in which it falls or the initial conditions away from axial symmetry, you will change, of course, this caustic, but its basic structure will not change. It will be some topological deformation of the caustic ring. And here again, you perturb it, but it's basically a stable object. Well, when I derived the existence of this caustic ring, we also call the tricusp ring because it has three cusps, you know. I assumed that the dark matter fell in what I call net overall rotation. Actually, the initial velocity field in the case of WIMPs and sterile neutrinos is irrotational. In that case, the caustic structure is like this. It is a different structure. We call it the tent structure. This is the case for rotational flow. Okay. I still have a bit of time, although not so much anymore. I was curious about these caustic rings, and I tried to predict where they are located. And for this, I used a model of self-similar infall that was originally proposed by Fillmore and Goldreich and by Bertschinger, and that Igor Tkachov and Yun Wang and I generalized to include angular momentum. So this is a bit a story of its own, but it predicts the radii of the ring to be in our galaxy. The first ring is at 40 kiloparsec. It lies in the galactic plane. The second ring at 20 kiloparsec. This is actually approximate, just as a mnemonic, you know, easy to remember. Then 40 divided by 3 is 13.3. 40 divided by 5, by 4 is 10, by 5 is 8, and so forth. This is for our galaxy. The radii in other galaxies would scale proportional to the rotation velocity of the galaxy, which is 220 kilometers per second in our galaxy, and one number per galaxy, which we call Jmax, which has number been estimated to be 0.26 for our galaxy. So, and I found actually observational evidence for this. And most of the evidence is based upon the fact that if you have a caustic ring in the disk of a galaxy, which is shown here in cross section, so this would be the bulge, this would be the disk of the galaxy. And then you have caustic rings in the plane, and you measure the rotation curve. You know, the rotation curve actually tells you about the gravitational field at various radii. We can show that at the caustic, there's going to be a kink in the rotation curve. It will dip and go up and go back down with two kinks. The kink is associated with the fact that the density diverges on the red line. So I thought I'd go look at rotation curves and see whether I can find kinks. Now, which rotation curve would you look at first, perhaps, is that of our neighbor called Andromeda, M31. And so this is its rotation curve. It was measured relatively recently in 2009 by Laurent Chemin collaborators. And in fact, it does have some structure. And I particularly, I tell you, okay, the rotation curve comes in three colors. Blue is, it says, okay, blue is approaching. You know, there's two sides to Andromeda. One, it's rotating. One, it's almost, we're almost in its plane, but not quite. One side is approaching us, one side is receding us. So one side is redshift, one side is blue shift. The rotation curve is obtained by obtaining the redshift and blue shift, so say the 21 centimeter line of H1. Okay, so you can measure both sides. Now, there is actually three bumps, one here, one here. The black line is actually the average of both. And then there is a bump here in the blue, but not in the red. These bumps roughly are in the correct ratios. This is a 30 kiloparsec, roughly this is about 15, and this is about 10. Not perfectly, but I draw your attention to the fact that this 30 kiloparsec is an enormous distance compared to the disk of M31. The disk has radius of order 30 kiloparsec. So this is much bigger than the disk, this bump. It occurs on both sides. So the diameter is 60 kiloparsec. It's an enormous thing. You should presume this is a ring because it occurs on both sides and has nothing to do with visible structure in M31. And people often think of these rotation curves as smooth, but you see, there must be something in M31 that is a ring with radius 30 kiloparsec, and there's another one with radius about 15 kiloparsec. And here you may fault the evidence because it only happens at one side. And this is, of course, unfortunate. But it's possible, perhaps, that the caustic ring here, the third one, lies somewhat outside the disk and is not picked up by the rotation curve. So there's some wiggle room, I guess. Will Kinney and I, we built a composite rotation curve out of that many galaxies, and we found evidence in this composite rotation curve for the first ring and for the second ring. I don't have much time, so I'm going to go a little fast. If you look at the outer galactic rotation curve of the Milky Way, there's evidence for the third ring at 13.3 kiloparsec. If you look at the inner rotation curve, the best high-resolution rotation curve is from a CO survey that was done in 1985. And you see these sharp rises. So here's a rise, represented by this line here, and this rise by that line, and this rise by that line. And what's striking about these rises is that they are sharp. They turn on a single data point, as you would expect from caustics. And also the number of rises is roughly consistent with the predictions of the model, which are shown at the bottom. Now, we are at 8.5 kiloparsec. This here is the prediction of the model. This is the nearest rise. Here I show a little dashed line. Well, I'll explain the little dashed line. So here is the top view of the Milky Way and the caustic ring that would be close to the sun, producing this rise in the rotation curve, close to 8, between 8 and 8.5 kiloparsec. If you look in the direction tangent to the caustic, you might hope to see the imprint of the caustic onto baryonic matter. So I went to look at various things and then found something triangular in the IRS map in this particular tangent direction. So I'm showing this tangent direction by this little dashed line. It fits perfectly the rise in the rotation curve within errors. And I don't know whether you see this triangle, so I'm helping you a little bit here. These are the vertices. And it's pretty sharp, this side is sharp, and this side is a little bit messed up. There's some other stuff going on. And this is at a different frequency in the IRS maps. And interestingly, this side becomes more fuzzy, but this side becomes a little sharper. No, I was told, yeah, that's great, but you don't show anything over there. And that's right. Try as hard as I might, I could not find anything there in IRIS or any other survey. So I often told people, let's suppose someone predicts that there are 2 unicorns in your backyard, and you find 1 unicorn. Is that evidence that your friend is correct or evidence that he is wrong? You only found 1 unicorn, that he predicted 2. But you should perhaps think that the unicorn is such an amazing beast. To find 1 is remarkable. To not find 2, maybe the other unicorn is hiding for some reason. But this issue got resolved thanks to thanks to Gaia. In Gaia, in fact, here's the Gaia map. You know, I'm sure you heard about Gaia, this fantastic satellite that is mapping the positions of billions of stars with great precision. So this is the Gaia sky map of the Milky Way plane. And stars are shown by light. And the dark is dust, which obscures the stars. And now you see this is where the triangle is that we saw in Iris. And actually you see it in other places too. But now on the other side, there's also a triangle. So now we see it on both sides. In Iris, we see only the left triangle, but in Gaia, you see also the right triangle. I tell you beforehand that it is not perfectly symmetric. This you see at roughly 80 degrees galactic latitude, and this you see roughly 90 degrees. But that's consistent with a shift of the caustic ring center away from the galactic center by about 700 parsec. Well, it seems good enough for me. I mean, you wouldn't then necessarily have expected that the caustic ring is perfectly aligned with the galactic center. Anyway, it is not. So I show here the left triangle in Gaia. I help you with the dots. And I don't know whether you see the right triangle in Gaia, but it's actually very sharp. I'll help you with the dots. No, my time has been over a little by 5 minutes. So something changed now, because before I used to think that the sun is outside, but now with Gaia, this ring has tilted, you see, and now if you interpolate between the two triangles, you find that the sun is most likely within this caustic structure. And that means that there are, outside, I used to think the sun was over here somewhere. There would be 2 cold flows, but now there's 4. And you can actually predict their velocity vectors. We call them big, up, down, little. And big, up and down are truly big, actually. The density in the big flow is of order 20 times the density normally attributed to the density to the dark matter at our location. And up and down are comparable, although less certain. Little is down by factor 10 or so. So here I conclude. Discrete flows and caustics are a robust prediction of cold dark matter cosmology, and there's observational evidence for caustic rings and galactic halos. And you will have noticed that if this evidence is correctly interpreted, it implies that the dark matter falls in with a rotational velocity field. And the irrotational velocity field would not produce the caustics for which we find evidence. So thank you very much for your patience and for your attention. And I'd like to hear questions.
Right, thank you, Pierre.
Okay.
So I'll open the, I guess I'm in charge of the questions. So I'll open the floor for questions. You can raise your hand or you can speak up.
It was a great talk, by the way. Really,
well, thank you.
Thank you.
Let me get started. So one thing I kind of wondered is, so this is something that happened in CDM. I mean, can we use some of these signatures to learn something new about dark matter, about something we don't know yet? I'm trying to see how this could be used to learn something cool about either galaxy formation or dark matter physics.
Yes, I claim that you do, in fact, but that's a different talk. But I'm happy to since you ask, to elaborate on this. Okay. Originally, I was interested in this question because ADMX, the axion dark matter experiment, is looking for axions. And I thought it may be helpful to ADMX to have some prediction for the velocity spectrum. And actually, this is a prediction, but which I was showing, I guess, here. But there's something else. If all this is correct, and I put this at the bottom here, then the dark matter falls in with a rotational velocity field. Actually, for a long time, this was really a bother to me, because you can show that CDM, ordinary CDM, is always irrotational. And the reason for this is that rotational modes get damped by the expansion of the universe, as you probably teach or learn in cosmology class. There is no rotation left over that is primordial. It has all been damped by the expansion of the universe. All the velocity fields that are produced by essentially Newtonian gravity. In Newtonian gravity, you will never produce a velocity field with a curl. It remains irrotational. And the main reason for this is that the force law is a gradient, right? The force in Newtonian gravity is the gradient of the potential, and the curl of a gradient is zero. And this has the effect that WIMPs and sterile neutrinos and any ordinary CDM has irrotational velocities and cannot produce these caustics. So this really bothered me for a long time. But now I think I know the answer to this question. The dark matter is neither, or at least in part, has to be axions. I have not stated this as part of my talk because I don't want to make too many claims at once. Okay, I claim that actually this means that the dark matter must partly be axions. It cannot be otherwise. And the reason for this is that axions thermalize by gravity. This requires some explanation, okay? And when they thermalize, they form a Bose-Einstein condensate. They go to the lowest energy state available to them. They rescatter, if you like. They change their states. And the lowest energy state for given angular momentum is a state of rigid rotation. And you can show that actually what's predicted by this argument I'm just giving, that will reproduce exactly, well, exactly, of course, I'm exaggerating exactly because there's some errors always, but really reproduces the phenomenology of these caustic rings. So I claim that the dark matter, there must be an axion component to the dark matter. I'm pretty sure about this. I'm not saying it's QCD axions, I don't know, but it has to be cold, highly degenerate, bosonic fluid. Yeah, it could also, there could still be WIMPs actually in addition. I'm not saying it's necessarily all. Sorry, I maybe overreacted to your question.
No, that's great. No, that's good, great. Rich has a question.
Yeah, thank you very much. The very enjoyable and thought-provoking talk.
Okay, thank you.
So with the rotation curves of the galaxies, so you talked about the little wiggles that you see in them. Typically, those are attributed to the spiral structure of a galaxy and have something to do with the spiral density wave.
Yes.
The origins of which are still unclear, whether they are long-lived or transient, and whether, what kinds of density perturbations might cause them. So I'm wondering, if you see wiggles like that, it usually sort of indicates that the ordinary matter is falling into the potential of whatever is causing it. So I'm wondering, have you thought about this in terms of the possible origin and explanation of spiral density waves? I know people have considered sort of dark matter clumps passing through the disk as ways of generating wave responses, but I haven't seen anything about what sort of spiral structure you should expect as a result of these caustics. So just wondering if you thought about that.
Yes, thank you very much. I don't know what I've thought correctly, but I think this is certainly a hard question with great potential for investigation. First, let me say the following. This is a high resolution rotation curve because it's made out of carbon monoxide. Carbon monoxide has a much shorter wavelength than hydrogen, which is 21 centimeter. And that's what makes the rotation curve higher resolution. The interpretation that bumps in rotation curve are due to spiral arms is quite old. I think it dates at least, I don't know, to the 60s. And in fact, if you look at this rotation curve, I don't have the picture with me, but you can find it easily in H1. You'll find that there is a bump here and there's a bump here. And in fact, this does agree with the location of spiral arms because one is called the Sagittarius arm and the other one is called the Scutum arm. But I'm saying, yes, that's true. In fact, these are prominent here too, but there's an additional set of rises. But maybe this is not what you are really asking about. I think so I'm saying, yes, of course, the spiral arms contribute and many other things contribute, but there's also evidence from these sharp rises for caustic rings and from the number. There's not, I think there's like 10 rises here. There's not 10 spiral arms. And the spiral arms would not produce, I think, sharp rises. They produce these broader bumps. But your question actually had another aspect to it. I think, can dark matter help explain the production of spiral waves? And this I don't know, but I think it's a very interesting question. I like to think, well, I'm not an expert on star formation, but I do read a little bit. I think star formation is fairly complex, and it may help. This is all I can say, is when these caustics go through the galactic plane, they move very slowly, but they may actually help formation of stars. Then you may ask, well, why is it a spiral? I don't know. People say spirals occur quite naturally, but the questions I think are very interesting. I don't know the answer to.
Yeah, I think if you put a ring-shaped perturbation in a gravitational perturbation in the disk and see how the gas responded in a simulation, you may get a spiral. I'm not sure.
It would not. People have told me, yes, you may very well be right. Yes, I haven't done it though. Someone else has to do it because people think I'm very highly prejudiced in favor of this. So whatever I do, I get accused of confirmation bias.
All right, thank you.
You're welcome. Thank you.
All right. Any other question for Pierre? Yeah, Mashami?
Yeah, hi. Great talk. I really enjoyed it. So a quick question for people that are doing directional searches for dark matter. If you have these, let's say, if we're in one of these caustics or close to them, and you think we have 4 separate flows, then is this really only a problem if most of the dark matter is axionic? But if some of it is non-axionic, would you still see a direction? Would you expect to see a directional signal? Have you thought about the implications of these 4 different flows, big up, little down?
So you look at whim detection, and you're hoping to see the direction of the flow.
That's right.
I think this is absolutely great, and I hope you will find them. You may think not that I'm not sincere, but actually I am, because I think that when you will see this, you will see this also in WIMPs. And that's because we believe, and we may be wrong about this, we believe that actually the WIMPs would be entrained by the gravitational field of the axions and flow the same way. In the absence of axions, they would flow irrotationally. But if there are sufficiently many axions, then we think they will flow along with the axions. So that if you have a directional detector, you'll find, I think, the WIMPs should flow like the axions, and you should see these directions. By the way, you probably noticed, I don't know, actually, maybe it wasn't clear because I didn't really say it. Normally, people, this is a view of the galaxy from the top. That's from the North Pole, okay? Actually, the galaxy is rotating this way. Normally, people say, so the sun is moving along with this rotation, and so the dark matter flows this way relative to the sun. But in this model, actually, is the opposite is true, because the dark matter is flowing in the direction of rotation and faster than the sun. And so it's actually opposite. Yeah, that's right. So okay. I'm sorry, maybe I again over answered your question, but I think that I know it's very difficult to detect direction of WIMP recoil and so forth, right? But if you could, it would be fantastic. It would be great. It would of course be great technical achievement, but it would also be very interesting, I think. And I don't think that you will find the common answer that the flux is largest in June and lowest in December. I think actually is the opposite.
All right, great. Thanks. Any more questions? All right. Well, I guess that's it. Well, thank you so much, Pierre, for this very interesting talk.
It was my pleasure. Thank you for having me.